Hello and welcome to today's session. My name is Roman Conver. I'm structural engineer at the SDC Verifier, and in this video we are going to explore the key aspects of the steel roof design in accordance to the Eurocode standard requirements. The agenda of this topics is short introduction about the structural failure, the problem solving with the SDC Verifier, how to apply the loads in according to Eurocode requirements, a load combination, and analysis of the steel structure. And if we are faced with some issues, we can optimize these cross sections or this structure that's possible with SDC, and as a result, we can grab all the information about the model setup and result into the total report, and it will be shown as well. At the end, I'm going to show you the use case of the real calculated steel structure and how it can be done with the SDC Verifier. So let's move on. Okay, so the structural failure can be catastrophic for the roofing structures, and it should be identified at the beginning of the design. So all these weak spots, the locations where the buckling can occur, and it can be sorted by the local buckling, which can accumulate into the global buckling and can lead to the complete structural collapsing. So solving those issues at the design stage provide the safe operation of the structure. We can avoid some costly errors because that's everything is money, and it can be ensured that it's a safe place for the people, and it also proved that the long-term solutions is possible with this structure. So a lot of aspects should be verified to be sure that this structure is strong enough to withstand under the more significant and extreme condition of the loading. So that can be the snow or even wind. Okay, so let's move on and talk about the background of the calculation of buckling. So buckling calculation based in general on the Euler equation, and this equation is can be treated as the Young modulus, which take into account the moment of inertia divided by the effective length of our memory. This effective length can be correlated and calculated depending how it's supported. So it depends how it's supported, and effective length, for instance, for the cantilever P will be equal to 2. So we need to multiply our L by factor 2 to take into account the proper effective length. That's about the mathematical equation, and in FEA calculations the logic pretty the same, but we calculate the arbitrarium scalar magnitude factor based on which we can multiply our load and reach the failure in the structure. So the critical buckling load, this is the supply load multiplied by the agent value, and this calculation method is available in almost all the softwares, FEA softwares, but with this case we cannot take into account the local effect if we use the beam element. So for this purpose I prepared this one slide, because all this steel structure, lattice structure, most of them can be executed with the beam elements. This is the quickest and convenient way how to do this. And yeah, we don't need to play with the geometry and overspend our time to prepare a model. Besides that, it's also speed up the calculation process. But with beam elements, it's not possible to take into account the local effect of the buckling, while with the 2D shell elements, that's possible. So as alternative solutions, we need to or calculate additional checks which take into account the shell elements for the weakest spots, or we can do the calculation based on the standard prescriptions. Yeah, that can be done by the spreadsheet, but this is also time-consuming process, and the solution is simple for this. We can use the SDC Verifier, which allows you to do all this step, all the cycles from the beginning to the end in one software. What I mean, so we can create the geometry, we can assign the proper cross sections for our beam elements. After that, we can recognize the structural members, because the standard says that the verification should be based not on the final element, while on the structural members. We can apply the loads, constraints, and execute the calculation based on the sim-centeredness trans solver. So this is pretty famous and convenient one to use. And since we have huge library of the standards, we can calculate beam member check directly in this software and be sure that our structure is well within the allowable limit or not. If no, we can execute the optimizations, we can sort the proper cross sections in order to provide the utilization effect within the allowable limits. So all this stuff is possible in one software, and today we're going to discuss this. And let's start from the loading, because this is also important aspect of the calculation. And we can go to the next slide, and here we can see that the basic loads is applied as the standard use gravity, and the roof pressure, which equal to 8.6 tons. This load applied as distributed load over the roofing beams. And on this picture we can see that the main roofing beams are mostly loaded compared to the end beams, because the load will be redistributed over the main, and that's good to mention. The next one, important load, this is the snow load, and this load is different for the different regions, and it can be calculated based on the snow load on the ground, which should be taken from the European map. For the right, you can see that how it's what the cold gradient and what the value should be taken for the proper country. This the snow load, the pressure of the snow should be calculated and based on the snow load on the ground, the shape coefficients and thermal coefficients. If we go to the next page, we can see the shape coefficients of the roof. It can be like mono-pitch roof, can be pitched roof, can be multi-span roof, cylinder roof, roof arbitrum, and the close to the taller construction works. So in the Eurocode standard, everything is prescribed and it can be easy to calculate. In our case, we need to use the mono-pitch rule, and the mu factor equal, since our inclination of the roof pretty small, approximately 3 or 5 degrees, we need to use 0.8 value. The next coefficients which should be selected, this is the topography factor, and is based on the location. I mean the we can consider three cases of it. We can consider the wind-swept topography, we can consider the normal topography, and also we can consider the shelter topography. So for all of them, we have different factors. And right now we are going to use the normal topography in this calculation. And last one, coefficients. This is the thermal coefficients. Based on Eurocode standard, it's like commonly used as value 1, but if you want to check in details, you can see the ISO 4355 and then more detailed information about this. So all those coefficients are predefined, and at the end for the Nazarene region, we can see that the snow load on the ground is equal 0.7 kN per square meter, and this value should be multiplied by the mentioned coefficient. This is 0.8 and 1, and at the end the snow load in total will be 560 Newton per square meter. So on this screen you can see that it's also taken into account. We applied for the main roofing beams the bigger value, while for the edge beams it's like a lower one. So that's about the snow load, and move on then to the next one. This is the wind load. This is also pretty complex load because it's based on the map of the basic wind speed depending on the countries, and this load, I mean the load which should be applied to the model, like wind pressure, which based on the peak velocity pressure and mean wind load, and this is, I would say, pretty complex calculation, since our civil structure should be splitted. In this case, this is the roof should be split into several sectors, and for them we need to calculate the external pressure coefficients. In this case, this is with the parapet roof, and as you can see that for zone F, G, H, I, this value is different. And how to calculate this? This is the ratio between the complete height of the structure and the parapet height. So that's the ratio. Based on this ratio, we need to find out those coefficients, and those coefficients should be multiplied by the peak velocity pressure. So at the end we faced with the complete number of the load, and on the left side we can see that wind load should be applied in the positive and negative direction. So that's also the requirements of the standard. In order to better visualize how it's implemented in the model, we have next slide, and here it's better shown that for the zone G it's applied for this location, for zone F it's applied at the corners, for zone H is applied here, and for zone I is applied at the end of the roof. Okay, next one, and typical one, I would say, this is the wind in the not X direction, while in the Y direction. So the logic is the same. We split our roof in those zones and we apply different magnitude for them. Okay, so next one, this is the second wind load and this load represents the impact on the knot roof, while the walls the wind impact on the wall also interesting, because we do not apply only wind for the front surfaces. We should apply it for all of them, and it also showed that our side surface splitted by the sections A, B, C, and also we need to apply the wind load and the back surface. For sure, we need to calculate the factors for this, as it was done for the roof structure, and these factors can be selected based on the ratio between the h divided by d. H means the height of the building, and d this means the width of the building. Sorry, this one. And based on this ratio, we figure out that in our case it should be this set of the factors, and we need to multiply the wind pressure by these factors. So from the left screen, you can see that the magnitude for the front walls and I would say the beginning of the side walls are bigger, while at the end of the wall and from the back side the values is smaller. So that's pretty nice to see it on the screen. And for the better representations, we can see the pictures which show that this is the wind for the front side, this is the wind from the back wall, and also the wind for the side walls. We did that, and we did for the both directions, for the x and y directions. So that's pretty the same approach how to apply the wind load for the steel structure. Okay, I think that's it about the loads, and we can go directly to the load combination. So load combinations in accordance to Eurocode as standard can be prepared in two ways using the SDC Verifier. So firstly, it's good to mention that we need to consider the loads of our our structure as permanent and variable actions. Permanent can be divided by the unvariable variable, so that's like difference between the safety factors. And for the variable action, for the variable actions, the partial safety factor even bigger, because this is the load which change magnitude during the time. Also, we need to take into account the reduction factors depending what category we are going to use. So that's how it works. Those load sets can be prepared in the Excel sheet, and after that copy directly to the window of the SDC Verifier. That's how it looks on the right side. Or another way and more convenient to prepare the load combination directly in the SDC Verifier. Okay, how it works? It's pretty simple. For our individual loads, we need to predefine the category of what load it should be. For instance, for the gravity, this is the permanent action, variable, this is like up to the user. Roof pressure, this is also permanent action. Snow load, we select the snow load on the building. Wind load, we also select the wind load. So that's easy to do, and from the right side you can directly see what the partial safety factor will be used for the set of the category for the calculation. So you can see that for the gravity 135, for the roof pressure 135, for the snow load 1.5, and the same as for the wind load. So I will say the creating load combination directly as the Verifier, this is the huge time saver and the more convenient way. By the way, it's also possible to adjust something, so a lot of space of modification. Okay, let's then move on. So after that, when we predefine our loads and load combinations, we need to recognize our structural members, since the standard says that the structure, the calculation, the code checking should be executed based on the structural members. And with the SDC Verifier, it's really easy. By clicking on one button, you can recognize all the structural members, all the members of your FEA model. And it's also good to know that SDC has the possibility to recognize the weak and strong axis. So we can also find out what the effective length for them. For instance, for this beam, we can see that this beam restrained in the horizontal direction but that one, and it's like splitted by 2. But for the strong axis, I mean for the z-axis, this beam has the same color, which means that it's not splitted. And the reason of it, because we don't have any support under this beam. So as you can see, for the y direction, the length will be like for this beam L divided by 2, but for the z directions, that would be the complete length. So SDC gives you possibility to recognize them, and in case of some modification, that can be also possible to adjust directly in the window of the Web Finder. So basically that's about the recognitions, and after the recognition we can calculate our structural elements, structural members in accordance to the Eurocode requirements. So this is the result of the steel structure. As you can see, that some location of the roofing beams do not pass the verifications, and for them the optimization is required. So we also can execute the optimization for those beams. So on this screen you can see that this is the original design, and this is the optimized design. So with the SDC Verifier we can select and find out the proper cross-section which help us to pass the standard requirements of the Eurocode, and select the proper cross-section for this. So basically that all these calculations are possible with the SDC, and at the end we can grab all the information about the model setup, about the results, and put them into the total report and store it. And if necessary, we can check ourselves if everything is prepared properly, predefined properly, or this report can be shared even with your client just to represent what scope of work was done. Okay, that's it about the presentation, and I hope it was useful for you. Then we can move on directly to the use case, and we can do this quickly with the FTA model. So here we are. This is the model of the steel structure which we are going to calculate. This model is completely executed with the beam elements. We can turn on the mesh size and see, rotate how it looks. Basically we won't spend our time to discussion about how to apply the loads, boundary conditions, and creating load combination. Just make sure that everything is there. So as you can see, online loads here, and also we can go to the load sets chapter, press created multiple, all load combination already created with the corresponding partial safety factor. We can press OK, and as next step, in order to start the member verification, we need to calculate our model. So press analyze on the job, and the static calculation is launched. Okay, model is calculated. We can turn off this window message, and in order to be sure that results already attached to our individual load, we can generate the plot, stress plot, for instance, for the complete structure. Select category stress equivalent and put full mode, press OK. And now you can see that since material of the steel structure is 355, and which correspond to the yield limit 355, and well within the global limit. But according to this criteria, it's not enough to be sure that your structure can withstand the acting loads. That's why we are going to execute additional calculation, which called beam member check, and it can be found directly in the standard library. So right mouse click, press add, and here we have the list of the different standards of verification. So let's go to the Eurocode free standard beam member check. And in front of us appear the window which should be upfront predefined. Needs related mostly to the characteristic of your structure. From the left side, represented values of the partial safety factors. From the right side, we need to predefine them characteristic. First one is the fabrication type. So we select all of them be rolled, press OK. Manufactured matte, hot finished, can be hot finish. Let's select the hot finish, press OK, and then fillets. We do not take into account the fillets, so we can leave as a 0. Then section area, since it's applied as 0, with this SDC will automatically calculate. And material type, for the yield 355, for the material S355, we use the it's already selected, and we use the S355. Press OK. Here we have the additional possibility to select for calculation the correlation factor, but we are going to use based on the standard requirements. We can select the different approaches for the calculation of vertical torsional buckling. So let's use default one, and we can select what the length of the lateral flexural and torsional buckling can be selected. So it can be as maximum between the distance of the strong and weak axis, or we can use the torsional length based on the beam member finder. So let's select the maximum one. And last one, settings, it's related to the unsymmetrical cross sections and cross section which is classified as class 4. So we can calculate them as class 3, and we can calculate asymmetrical just to obtain some brief understanding of the behavior and what value will be for those cross section. In this use case, we don't have such as mentioned, but just for your understanding, that's possible to estimate the preliminary state of those structures. So the characteristic already predefined, and what left to do is run the beam member finder, and we can do it directly from this window. So press this button, open beam member finder tool, and here appear the window of the beam member settings, what the joints should be recognized, because the beam members based on the joint finder, and it support 1D, 2D, 3D connections. So what we need to do, just simply press find. Do we want to update our joints? Yes. And our joints recognized already. So our members recognize here too. So all members are recognized in the strong and weak axis. As we discussed previously, we can highlight all of them in the Y and also Z direction. So this is the Y direction. We consider the length in the weak axis, and as you can see here, it's splitted. And for the Z direction, it also well recognized, and this beam is continuous, which means that our structural members and the weak and the strong axis properly selected. So the distance between the this column and this column will be taken as the effective length. Okay, so press OK, and we can close the standard. Press OK. Then the standard is already automatically added to our library, and we can expand to see what is inside. So first 8 or 9 standards represent the settings and availability to check different cross-section types. So that can be circular beam, tubes, rectangular beam, tubes, I-shape, T-shape, and so on. So you can see it directly. Then we have classification of the flange and web separately, and after that we calculate what the critical one and what the class should be applied to this structural member. And then we can see the list of the standard which will be checked with this calculation. So this is the shear check axial, bending axial, buckling, compression, torsional, lateral torsional buckling, and at the end we will have the buckling and overall check, which show the maximum overall results in this list. So let's run the calculation. For this we need to generate the picture or generate the table. So let's generate contour plot, select the proper load. In this case it will be in load group envelope, which contains all load combinations. Press OK and press OK. So the calculation already started. SDC will read the results from the output set, and we can run the beam member check. Voila. So this is the results of the beam member verification. And as you can see, the roofing beams, the several location has the utilization factor above 1, which means that we should optimize those zones and select the proper cross-section to withstand the snow load and wind load, extreme loads from these scenarios. Just to be more precise, we can build a table and see what the maximum utilization factor. So that's the build table. Go to the load group, load sets, press OK, and fill table. And here you can see that extreme table shows the maximum value over the complete structure is 2.16, which is quite a lot. So the one way what should be done to reinforce this structure, select the cross-section which can withstand those loads. And SDC can help us with this. So we have this optimization modulus, which I would say optimize the engineering work, because with this modulus we can predefine what type of the optimization we would like to execute for which loads, and SDC at the end give you answer. Then it's a more convenient and easiest way to do this and to receive the proper results. So let's add optimization, and here we need to add one, and here we can see that what the optimization can be executed. It can be based on the beam rule, plate buckling, plate element rule, or weld strength check. So in our case this is the beam rule. We need to predefine the standard and check. That would be like Eurocode 3, buckling and overall, and also we need to select the parameter. Then we need to apply the limits. So we want to receive the results lower than value 1. And then we need to select what the structural should be optimized. In our case, this is the roofing beams. The first one, this is AP 500. Press OK and select what the possible cases should be checked. we can press this button, and this is the button which opens the library of the cross sections. So here you can see the huge list of the cross sections supported by the SDC Verifier. And from the left side, we can find the information about the type, width, like general dimension of the structure, area, moment of inertia, and from the right side there's more detailed information. And if I just simply clicking by this, we can see that it's changed. Since we use the I shape, I would like to replace this with the same, and the easiest way, select the filter, select the I shape, and now all the I shape is sorted. So since we used I shape, we can select the bigger one. So a 600, for instance, and IP 750. That's two cross sections which we are going to check for the main moving beam. Press OK, and the second group for the validation will be another beam, another roofing beam. This is IP 360. Press OK. Press OK, and let's open one more time in the library. Sort them. And select IP 400. Probably this is the closest one. Press OK. Press OK. Press OK. So the structure which need to be verified and the possible cases we already predefined, you just need to press OK and select the optimization and press calculate. SDC will automatically run the calculation of optimization. A few words about the optimization approach. So this is not the reverse calculation. We just replace the characteristic of the cross sections to existing one, and all internal forces which were calculated previously didn't change. So that means that we at the end we obtain some approximate results, and then we need to update those cross sections and recalculate model again. So we receive the results for this calculation, and what we can see, we can check the all results, we can check optimal, can check all results, and now we can see that for IP 500 the optimal case is the IP 750, while for the IP 360 optimal one IP 400. That's how it represented. We can press OK, and with SDC we can also update our model automatically. We don't need to select all these beams manually. We can press change them. Press yes. And it should be automatically updated. Press OK and close our optimization. So as you can see, the cross section already updated. We can highlight with the different properties, and just to synchronize our model with the calculation box, we press update the model, continue results, OK. So to be sure that the model is automatically updated, we go to the model tree, open properties, and then at the end we can see the optimization beam with the old name and new name, and we can turn on to turn off and see that it's already updated. Also the secondary beams already updated here. So model complete. And what we can do next, just to be sure that our structure is properly updated and the result will be while within the allowable limit, we need to recalculate it and execute beam member check again. So let's add new job, or we can even copy this one. Copy job 2. Press OK. Press analyze. Yes. And the model is calculated, and then we need to implement one more standard. So let's execute the same approach, Eurocode 3 standard, just to have the stored results of the previous results and the current results. So we will select previously, roll it for the all, for finished, fill at 0, area, materials predefined. So that's it probably. Press OK. And we need to go to the end of the buckling and overall standard. Select the control plot, select the proper load. So we need to select the job 2, load group, load sets, press OK, press OK. And as this, you run the beam member check with the updated cross section. It will take several seconds, I would say, but I hope the results will be well within the allowable limit. And after the picture generating, we will build the table to see the detailed results. Okay, let's turn on this window, and now we can see that our proofing beam below the allowable limit. Okay, let's generate the table. Select the load group, job 2. Okay. And the maximum value of the roofing beams, which mostly loaded, that's 0.96, which means that we're fine with this calculation. Okay, so basically that's it about the use case, and maybe we can summarize everything during this discussion. So with the SDC Verifier, we can create the FA model from the scratch. It can be simple beam model or even 2D, 3D. The model with the 2D, 3D beam elements. We can apply the loads, we can predefine the constraints, we can execute static calculation with Nastron solver and check the stress level in the structure. But in order to be sure that our results well within the allowable limit, for the roofing structure, we need to additionally calculate the beam member check according to Eurocode 3 standard, and that's everything possible in one place. We can do this directly as the SDC Verifier, and as the last step, which I forgot to mention, that we can generate the total report. So we can go to the design, add full designer tool, and this is the window of the report designer. We can fill in data about the client, about the engineer who is working on this project. We can generate this page, can even show the front picture of our structure. We can generate material properties, complete model setup. Like this. And we can add the results of the beam member check for our structure. So let's use the last one, the reupload. Log. Select the log. It shouldn't be content, it should be load group. Okay, and let's generate. All these views can be adjusted, it can be more detailed, more general, so it's up to user. So all this information can be sorted and put it in a way you would like to, and stored in your engineering library or shared with your clients. After that, we can simply export it to the PDF or Word document. So that's how it looks. Okay, thank you for your attention and see you soon. Bye.